Hello. In this video, I'll talk about the basic strategy with a proof by contrapositive. So this is our second proof technique besides just a direct proof. So I'll talk through the strategy of how we do something by how we prove something by contrapositive, and then we'll also take a look at a few examples, in particular results 3.20, 3.21, and 3.22. I'll also talk a bit about why we would want to use a proof by contrapositive, or how we can recognize that this is the right strategy for a given statement. So just like in a direct proof in the last section, we were mostly concerned with proving statements like for all x in some set S, P of x implies Q of x. That this was mainly the statements we were looking to prove. And in a direct proof, we assume P of x and show Q of x follows. That was the idea for a direct proof. In a proof by contrapositive, rather than assuming P of x, we assume not Q of x. So I'll say we assume not Q of x and show not P of x follows. So why does that work? Well, remember that P of x implies Q of x, that's our implication, is equivalent to its contrapositive. It's equivalent to not Q of x implies not P of x. These two statements are equivalent, right? They share the same truth value for all possible truth values of their underlying statements. And so if I can show this, if I can show this is true, then this must also be true because they share the same truth value. So this offers us another way to prove statements like this, implications, and in particular universally quantified implications, by instead proving their contrapositive. And again, what this looks like proving the contrapositive, well, this is still we're proving the contrapositive directly. I know that sounds weird, but what I mean by that is it's the same idea. Here we have an implication we want to prove, so we assume the hypothesis and show the conclusion follows. When we're looking at the contrapositive, we're assuming not Q of x and showing that not P of x follows. So this is the idea. Let's look at an example. So result 3.20 says let n be an integer. So there's our set, so n is an integer. If 7n plus 3 is an odd integer, then n is an even integer. So here I could let my P of n be the statement 7n plus 3 is odd, and Q of n would be the statement n is even. So what we're trying to prove here is that for all n in the integers, oops, just a comma there, for all integers n, P of n implies Q of n. So the first step for a contrapositive proof is to identify the contrapositive. And so in this case, it would be for all n in Z, not Q of n implies not P of n. So that is, so restating this in words now, the contrapositive would be if not n is even, so if n is not even, that would mean n is odd. So if n is odd, then 7n plus 3 is not odd, it's even. Then 7n plus 3 is even. So this is the result that we're actually going to prove, and because this is the contrapositive of the original statement, we're proving the original result here. We're proving that. So let's actually prove this. So remembering back to direct proofs, here I want to assume n is odd. So I'll say assume n is odd. And remember what that gives me. That tells me that n can be written as 2k plus 1 for some k. then n equals 2k plus 1 for some integer k. So that gives me some leverage to work with. Now I have an expression for n that I can plug into 7n plus 3. So 7n plus 3 is 7 times 2k plus 1 plus 3. And doing some algebra, that gives me 14k plus 7 plus 3. So that's what, 14k plus 10. And remember, we want to show that this is even. So we'll factor out a 2. So this is 2 times 7k plus 5. And now I can finish up my proof. I've shown that 7n plus 3 is twice some other integer, so that means it's even. Hence, 7n plus 3 is even. Right? It's obvious that 7k plus 5 is an integer. It's okay to not have to write that. I know we did that when we talked about direct proof, but this is just to get you in the hang of writing down everything that you know and making sure that everything is satisfied. But hopefully that's clear why that shows that 7n plus 3 is even. And that's the proof. Right? So again, we showed if n is odd, then 7n plus 3 is even. Contrapositive of that, equivalent to the original statement, is that if 7n plus 3 is odd, then n is even. And so we've actually proved this result. Let's look at another example. This is result 3.21. Let n be an integer. If 5n plus 2 is an odd integer, then n is an odd integer. So again, we're going to do this by contrapositive. So think about the contrapositive of this implication. That would be not q of n. So if n is even, then 5n plus 2 is also even. Right? Not odd, that's even. And not odd, that's even. And we're going to do this in very much the same way that we just did the last example. So let's prove this. Proof. I'm going to assume n is even, and then write it. So once we know n is even, then we can write it as n equals 2k for some integer k. And then think about what we want to do with that. It's the same idea as the last one. Then I'm going to substitute that into 5n plus 2. So 5n plus 2 is equal to 5 times n is 2k now, plus 2. So that's 10k plus 2. Again, we can factor out a 2. Remember, I want to show that this is even. 5n plus 2 is even. This is 2 times 5k plus 1. Hence, 5n plus 2 is even, since we've written it as twice another integer. Did it. Done. So I want to mention something here, and that is, how do we know when to use a proof by contrapositive? This is a pretty frequently asked question in this class, is how do we know what proof technique to use? We're going to learn a lot of different proof techniques. And so specifically, how do we know when to use a proof by contrapositive? Well, as you do more of these, you'll build up an intuition for when to use a contrapositive. But I'll mention something here, that suppose we tried to prove result 3.20 directly. So suppose we wanted to show this directly. Well, what would be our assumptions and what would we be trying to prove? Well, the hypothesis would be 7n plus 3 is an odd integer. So we would assume 7n plus 3 is odd. And we would want to show that n is even. Show n is even. So in this case, we would be able to write 7n plus 3 as 2k plus 1, right? We'd be able to say 7n plus 3 equals 2k plus 1 for some integer k. And then we'd have to somehow take that and show that n is even. Well, look at what happens when I try and solve for n here. If I want to show n is even, I'd be trying to solve for n and hopefully be able to factor out a 2. If I solve for n here, I'd get what? N equals, subtract 3 from both sides, 2k minus 2 divided by 7? Well, I mean, I could try factoring a 2 out. I see a 2 here. I could write this as 2 times k minus 1 over 7. But k minus 1 over 7 is not always an integer. And so I couldn't say that n is even here. That doesn't follow from what I've written. And so trying to do this one directly, it really doesn't get us anywhere. We kind of get stuck here. We'd have to then prove that k minus 1 over 7 is an integer, or, I mean, it's not always an integer. So we'd have to figure out what k values actually give us integers here. It'd be a whole mess. So this route doesn't really work. This just doesn't help. The idea here is that we don't have enough leverage on 7n plus 3 being odd. We could prove this one directly if we use a proof by cases argument, which we'll get to next. But really, this is just, it's not feasible. So you can try it directly. And a lot of creating a proof is about exploring your options, trying things, and see if they work out. So you can try any proof directly. But if you get stuck like this, try something else. In particular, try a proof by contrapositive. So that's one way to be able to do this. I'll give another example of this. Let's look at one more result. Let x be a real number. If x cubed plus 3x squared plus 2x plus 1 is less than or equal to 0, then x is strictly less than 0. So think about what I would have to prove if I was doing this directly. I would assume that this cubic polynomial here is less than or equal to 0, and then I'd have to show x is strictly less than 0. So while maybe if you're really good at solving cubics, you could do this, you could do it this way, you'd figure out that x could only take certain values in order for this polynomial to be less than or equal to 0, and then you'd show that those values are all strictly less than 0. There is a route to doing this directly, but it would involve solving this cubic equation, and or cubic inequality, sorry. And I don't know, that seems difficult. I don't want to do it. And so instead we think about the contrapositive. So think about the contrapositive of this. If x is greater than or equal to 0, then x cubed plus 3x squared plus 2x plus 1 is opposite of less than or equal to, is strictly greater than 0. So remember, something like less than or equal to, if we negate this, this turns to strictly greater than. So flip the sign and get rid of the equality possibility. And something like strictly less than 0 would go to greater than or equal to when you look at the negation. So here's the contrapositive, and now we have a leg to stand on. We have more leverage. We know we can assume that x is greater than or equal to 0, and hopefully we can mess with inequalities a little bit and show that this has to be strictly greater than 0. So let's prove it. assume x is greater than or equal to 0. And I want to show this polynomial strictly greater than 0. So I'll look at term by term here. I know x is greater than or equal to 0, so certainly x cubed is greater than or equal to 0. So I can say then x cubed is greater than or equal to 0. X squared will be greater than or equal to 0. And x will be greater than or equal to 0. So, and actually I can say more than just x squared is greater than or equal to 0. I could say 3x squared is greater than or equal to 0, right? Take something greater than or equal to 0, multiply it by 3, it's still greater than or equal to 0. And I could say 2x greater than or equal to 0 here. So look, each of these terms is greater than or equal to 0, and I'm adding them together. So x cubed plus 3x squared plus 2x, that's all going to be greater than or equal to 0. If I add 1 to this, it'll be strictly greater than 0. So how we can say that with inequalities? So this will be greater than or equal to, if this whole bit is greater than or equal to 0, I can say this whole thing is greater than or equal to 1. And 1 is strictly greater than 0. So now I have x cubed plus 3x squared plus 2x plus 1 is strictly greater than 0. And that proves it. Okay, yeah, do I want to say anything else about this proof? We'll do more of these inequalities. There will be some more examples about this. This is the general strategy, is to get a bound on x and then apply that to individual terms and combine them all together to show what you want. Okay, I think that's it for this video though. I'll talk in the next video, talk about proving biconditionals using the contrapositive. I'll see you there.